This research investigates the electrical properties of knitted stitch patterns in order to select stitch patterns that can be used as strain sensors and interconnects in knitted wearable circuits for human joint motion sensing. Knitted sensors are gaining traction because their inherent flexibility makes for comfortable wearable sensors. Machine knitted fabrics are made on knitting machines with rows of needles, called needle bids, that form yarn into interlocking knitted loops. The three basic stitch types, knit, tuck, and miss, plus stitch transfer actions, can be combined to form stitch patterns, which are modules of knitting instructions that repeat periodically to form a knitted fabric. When knitting using electrically conductive yarn, changing the stitch pattern can change the fabric's resistance and response to strain. To broaden our understanding of this relationship, we compare the electrical performance of 13 basic stitch patterns. Of the 13 stitch patterns, 9 are single bid stitch patterns and 4 are double bid stitch patterns. The samples are knitted as Wale-Wise or vertically oriented rectangular patches using conductive silver-coated polyamide yarn. Each conductive patch is surrounded by non-conductive spandex yarn to simulate the integration of the conductive patch in a garment. To understand the electromechanical properties of the knitted fabric under repeated stretching, each knitted sample undergoes a linear cyclic strain test at 90% strain for 50 cycles. The output voltage across the knitted sample and the encoded data from the stepper motor are normalized according to the initial voltage and initial length of the sample. The electrical performance is evaluated based on the gauge factor, working range, and resistance. The gauge factor reflects the sensitivity of the knitted sample. It is defined as the ratio of the normalized voltage to the normalized length. The working range is the practical range of the strain sensor that produces the maximum positive change in voltage. To compare the size of the working range of different stitch patterns, we use the difference between the start and end of the working range as expressed in percentage points. Both the gauge factor and the working range are calculated based on the loading cycle. The resistance measurements are taken before the cyclic strain test. To account for the varying lengths of different samples, the resistance measurements are normalized by the conductive patch length. An ideal strain sensor should have a high gauge factor and large working range so that it can sense a wide range of motion. An ideal interconnect should have a low gauge factor and low resistance so that it has negligible resistance regardless of strain. Our results show that interlock times 2, the stitch pattern with the highest gauge factor, is 7.16 times more sensitive than linen stitch, which is the stitch pattern with the lowest gauge factor. The working range of interlock times 2 is 2.9 times larger than the working range of full cardigan, and the resistance of purl is 3.5 times higher than the resistance of interlock times 2. Based on our results, RIP 1x1 and interlock times 2 are the best strain sensor candidates because of their high gauge factors and moderate to large working ranges. Linen stitch and full cardigan are the best interconnect candidates because of their low gauge factors and relatively low resistances. The results show that using different stitch patterns can allow us to customize the electrical performance of knitted conductive fabrics, allowing a single conductive fabric to have different properties and potentially different electrical functions based on the stitch pattern. To demonstrate how this can be applied in a wearable device, we use RIP 1x1 and linen stitch to knit the strain sensor and interconnects of a circuit to sense the bending action of a knee joint. Thank you for watching this video. For more details, please refer to our research paper.